The sun looks calm from 150 million kilometers away, smooth, golden, almost peaceful. But beneath that familiar light, magnetic fields twist until they snap, launching radiation and billions of tons of plasma across the solar system. Most storms pass unnoticed. One powerful enough, however, could disturb satellites, silence radio signals, damage transformers, and push entire power grids toward failure before the sky even begins to glow with aurora. This is not a story about the sun destroying Earth. It is about how a civilization built on electricity can become vulnerable to a star that has always been restless. Thank you for spending part of your day or night here. Please share in the comments what time it is where you are and which part of the world is listening with you. If calm, deeply researched science feels worth supporting, leave a like, subscribe for more journeys like this, and share the video with someone who enjoys the hidden forces shaping our world. Now, let the quiet surface of the sun fall away and enter the storm beneath it. The sun appears almost perfectly calm from the distance of Earth. Its round edges clean, its light is steady, and its presence seems so constant that it becomes part of the background of every day. It rises, crosses the sky, and sets with a rhythm older than memory. From the ground, it resembles a smooth golden disk, a fixed source of warmth and light that has shone for billions of years. Yet this appearance is one of the most persuasive illusions in nature. The visible surface is not solid, the light is not entirely gentle, and the quiet is only a result of distance. Beneath that bright face lies a vast moving body of plasma, twisted by magnetic fields, stirred by rotation, and capable of releasing energy on a scale no event on Earth can easily match. The sun is not a lamp suspended in space. It is a star, and a star is a restless machine built from gravity, heat, charged matter, and time. At its center, gravity presses matter so tightly that atomic nuclei fuse together. Hydrogen becomes helium, and a small part of the original mass is transformed into energy. That energy begins a long journey outward, passing through dense inner layers before reaching the surface and escaping as light. The process is continuous, but the result is not simple. Energy does not rise through the sun in a perfectly even stream. Hot material moves, cooler material sinks, and great currents turn through the solar interior. The star rotates as well, but not like a rigid sphere. Its equatorial regions complete a rotation faster than its higher latitudes. This uneven motion stretches and winds the magnetic field. Over time, the field becomes increasingly complex, like invisible threads being pulled, folded, and wrapped around one another inside a churning ocean. The visible surface, called the photosphere, is only the layer from which most sunlight escapes. It has a grainy pattern because enormous cells of hot plasma rise, release energy, and sink again. Each cell lasts only a short time, but together they cover the surface in constant motion. The sun's apparent smoothness disappears when seen in detail. Dark sunspots interrupt the brightness. They're cooler than the surrounding surface, though still intensely hot, and they form where strong magnetic fields interfere with the upward flow of heat. Some are larger than Earth. Some appear in clusters. Their number grows and declines in a repeating cycle that lasts about 11 years, revealing that the sun has periods of greater and lesser activity. Even during quiet phases, however, the star never becomes truly still. Above the photosphere lies a changing atmosphere. The chromosphere forms a thin glowing layer, and beyond it stretches the corona, a pale outer region visible from Earth during a total solar eclipse. The corona reaches far into space, forming the beginning of the solar wind. It is also unexpectedly hot. Although the visible surface is several thousand degrees, the corona reaches temperatures of more than 1,000,000 degrees. The exact details of how this outer atmosphere is heated remain an active area of research. Magnetic waves, tiny bursts of reconnection, and other processes all appear to contribute. This shows that the sun does not release energy only through steady light. Magnetic energy moves upward, changes form, and heats matter far beyond the surface. The corona is therefore both an atmosphere and a warning. It is the place where the sun's magnetic structure becomes visible through arches, streamers, and loops. These shapes are made of plasma held along magnetic field lines. They can remain stable for days or weeks, suspended far above the surface, while energy quietly accumulates around them. The calm view from Earth hides this tension. Distance turns enormous motion into a silent image. A loop rising tens of thousands of kilometers may appear as a small curve. A sunspot group large enough to swallow several planets may look like a faint mark. A sudden burst of radiation may cross the space between the Sun and Earth in only a few minutes, yet the star gives no sound that can travel through the vacuum. Everything unfolds in silence. The sun's light arrives as usual, even while magnetic fields are being twisted toward instability. This is part of what makes solar danger difficult to sense. Earth's civilizations have always depended on the sun, but for most of history they have known little about its changing behavior. Early observers see spots moving across its face, though many struggle to accept that the supposedly perfect sun can contain blemishes. Later instruments reveal that these marks are linked to magnetic activity. The smooth golden disk becomes a layered, dynamic environment. It shines in visible light, but it also emits ultraviolet radiation, X-rays, radio waves, and streams of energetic particles. Most of this activity causes no crisis at the surface of Earth. The planet is not exposed without protection. Its atmosphere absorbs much of the most harmful radiation, and its magnetic field diverts many charged particles. The same solar activity that might threaten technology also creates auroras, curtains of light that spread across polar skies when energetic particles enter the upper atmosphere. This dual nature makes the sun difficult to describe in simple terms. It is both giver and hazard, stable and variable, familiar and deeply strange. Its ordinary light powers photosynthesis, drives climate, and supports nearly every food chain on Earth. Its occasional eruptions can disturb satellites, navigation, radio communication, electrical grids, and the wider systems that modern civilization depends upon. The danger does not come from the sun suddenly changing into something entirely different. It comes from the normal behavior of a magnetic star. Solar storms are not accidents outside the design of the system. They are natural releases of stored energy. The same plasma that carries heat upward also carries electric charge. The same rotation that helps shape the solar cycle also twists the magnetic field. The same corona that flows gently outward as solar wind can also launch vast clouds of magnetized matter. The sun remains itself throughout. Its hidden danger grows from the very processes that allow it to shine. Scientists watch this activity continuously, because the line between quiet and disturbed conditions can change quickly. A region of tangled magnetic fields can remain stable, then release energy through a process called magnetic reconnection. Field lines break and reconnect in a new arrangement, converting magnetic energy into heat, radiation, and motion. The result may be a solar flare, a sudden flash across a wide range of wavelengths. It may also be associated with a coronal mass ejection, a vast eruption that throws plasma and magnetic field into space. These events are related but not identical. A flare sends radiation outward at the speed of light. A coronal mass ejection travels more slowly. though the fastest can cross the distance to Earth in less than a day. The first sign may therefore arrive long before the main cloud. This sequence gives solar storms a strange shape. The warning can travel ahead of the danger, like light preceding a silent impact. Yet even that warning is not always easy to interpret. Not every eruption points toward Earth. Not every Earth-directed cloud carries a magnetic orientation that strongly couples with the planet's field. Not every strong solar event causes severe damage. Risk depends on speed, density, magnetic structure, timing, and the condition of Earth's magnetosphere. The Sun does not aim. It erupts into space, and Earth happens to move through one small region of that space, for long periods. The planet remains untouched by the most powerful events. Then a large eruption crosses the right path, and the quiet relationship between star and civilization becomes suddenly visible. That possibility remains hidden on clear days. The sunlight falling across oceans, cities, forests, and fields carries no obvious sign of the forces moving above the solar surface. Power lines hum, satellites circle, data crosses continents, and navigation systems measure position with extraordinary precision. All of it operates beneath a star that appears smooth and patient. The deeper truth is less comforting but more accurate. The Sun is calm only in the way a vast sea may look calm from a distant shore. Its surface is always moving, its atmosphere is always flowing, its magnetic field is always changing. Most of the time, those changes pass harmlessly into space, at rare moments. They gather into eruptions large enough to reach across the emptiness between worlds. The first mystery is therefore not whether the Sun can become dangerous. The evidence already shows that it can. The deeper mystery is how often its hidden tension rises to the level that matters, how much warning Earth receives, and how a civilization built on fragile electrical systems responds when the quiet face of the Sun finally breaks. Beneath the visible brightness of the Sun, matter no longer behaves in the familiar way found on Earth. The star is made almost entirely of hydrogen and helium, but those elements do not remain as ordinary gas. The temperatures are too high, the collisions are too violent, and the energy passing through the interior is too intense. Atoms cannot hold themselves together in the usual form. Electrons are torn away from their nuclei, leaving positively charged ions moving among free negative electrons. This electrically active state of matter is called plasma. It is often described as the fourth state of matter, after solid, liquid, and gas, though in the wider universe it is far more common than any of the others. Stars, glowing nebulae, much of interstellar space, and the flowing outer atmosphere of the Sun are all shaped by plasma. Earth seems to be a world of rock, water, and air. But the cosmos is largely a realm of charged particles responding to fields that cannot be seen. The Sun therefore does not resemble a solid sphere with a burning surface. It is closer to a self-gravitating ocean of plasma, layered by pressure and temperature, moving in currents that rise, sink, twist, and shear. Near the centre, matter is compressed to an extreme density. Atomic nuclei are packed closely enough for fusion to occur, and radiation is produced in enormous quantities. Farther outward, the pressure becomes lower, but the material remains ionized. Energy passes through the inner radiative zone mostly by photons being absorbed and re-emitted again and again. A single packet of energy may take an immense span of time to work outward, because it cannot travel in a straight path through such dense material. Eventually, the energy reaches the convective zone, where the plasma itself begins to carry heat. Hotter material rises toward the surface, releases part of its energy, cools, and sinks again. This overturning motion forms the deep rhythm beneath the visible photosphere. It also creates the conditions from which magnetic complexity grows. Plasma differs from ordinary gas because it is controlled not only by pressure and gravity, but also by electric and magnetic forces. Each charged particle responds to those forces. A proton moving through a magnetic field does not simply continue in a straight line. Its path curves. An electron curves in the opposite direction because it carries the opposite charge. In a weakly ionized gas, only a small number of particles behave this way. But in the Sun, the material is so thoroughly ionized that the behavior of the whole fluid becomes tied to electromagnetic fields. The particles collide often, yet they also move collectively. They form currents. Those currents create magnetic fields. The magnetic fields then guide the currents in return. Cause and effect fold into one another, creating a system in which matter shapes the field, and the field reshapes the matter. This relationship is described by magnetohydrodynamics, the study of electrically conducting fluids in motion. The term is long, but the central idea is simple. Solar plasma flows like a fluid, while at the same time carrying and responding to magnetism. The result is far more complex than ordinary weather. In Earth's atmosphere, winds move because of differences in heat, pressure, and rotation. In the Sun, similar large-scale motions exist, but magnetic tension adds another kind of force. A magnetic field can be stretched, compressed, twisted, and bent. It behaves in some ways like a set of invisible elastic bands embedded in the plasma. This comparison is not exact, but it reveals why magnetic energy can build. When the plasma moves, the field lines often move with it. They are carried upward, dragged sideways, and wrapped around the rotating star. The field does not remain smooth. It becomes tangled because the plasma itself is turbulent. At the surface, the tops of convection cells appear as granules. Each granule is a bright region of rising hot plasma surrounded by darker lanes where cooler material descends. These patterns last only minutes, yet they are part of a much deeper circulation. Larger flows spread across broader regions. Rotation bends them. Different latitudes move at different speeds. The northern and southern hemispheres develop magnetic structures that change over the solar cycle. All of this begins with the fact that the Sun's matter is electrically charged and free to move. A solid object would resist such continuous reshaping. A neutral gas would not store magnetic energy so efficiently. Plasma allows the Sun to act as both furnace and dynamo, releasing heat while building fields through motion. Even light is affected by this environment. Photons passing through plasma interact with charged particles and atoms in different states of ionization. Certain wavelengths are absorbed or emitted depending on the conditions. By studying the Sun in visible light, ultraviolet, X-rays, and radio waves, scientists examine different temperatures and layers of the solar atmosphere. Each wavelength reveals another part of the plasma's behavior. The bright visible surface shows convection and sunspots. Ultraviolet observations trace hotter structures above it. X-rays reveal regions heated to millions of degrees, especially around active magnetic zones. Radio signals can follow energetic electrons moving through the corona. The star changes appearance across the spectrum because plasma does not shine in only one way. Its temperature, density, motion, and magnetic environment all determine what kind of radiation escapes. This is one reason a solar storm can begin invisibly to human eyes. A region may look only slightly disturbed in visible light while producing intense radiation at shorter wavelengths. Charged particles may be accelerated along magnetic fields before a larger eruption is fully developed. The plasma carries information about the event, but that information must be read through instruments. The Sun's ocean is not made of water, and its waves are not ordinary waves. Disturbances move through it as pressure pulses, magnetic oscillations, and combined modes that depend on both matter and field. Some waves travel along magnetic loops, others pass through deeper layers. By measuring vibrations on the surface, scientists can infer conditions inside the Sun through a method called helioseismology. The name reflects a comparison with earthquakes, but the Sun has no crust to fracture. Its entire body rings and pulses with waves produced by turbulent motion. Those waves reveal patterns of rotation and circulation hidden below the surface. They show that the plasma ocean has structure, currents, and changing depths, even though it cannot be touched directly. The charged nature of plasma also allows energy to move in sudden, concentrated ways. Electric currents can become narrow and intense. Magnetic fields can press against one another with opposite directions. When the arrangement becomes unstable, the system can reorganize rapidly. Energy that has been stored gradually may then appear as heat, radiation, and high-speed particles. The eruption itself may last minutes, but the preparation can unfold for days. A sunspot group grows. Magnetic loops rise. Plasma follows the field into arches above the surface. Currents strengthen. The region becomes crowded with energy, yet it may still appear suspended in balance. This balance is never entirely still. Plasma circulates along the loops. Waves pass through them. Small bursts occur. The boundary between stability and eruption becomes increasingly delicate. None of this would be possible in the same form without free charges. The Sun's danger is therefore rooted not only in its heat, but in the kind of matter that heat creates. Extreme temperature strips atoms apart. Separated charges move. Moving charges generate currents. Currents create magnetic fields. Magnetic fields trap, guide, and accelerate more charged matter. From this cycle emerges a star whose outer layers can store energy far beyond what their calm light suggests. The plasma also refuses to remain confined. At the edge of the corona, the Sun's gravity and magnetic control cannot hold every particle forever. Some escape outward, carrying the magnetic field with them as the solar wind. This flow surrounds the planets and fills the solar system with a thin, continuous extension of the solar atmosphere. Earth does not orbit in empty space. It moves within this expanding plasma, protected only partly by its own magnetic field and atmosphere. Most of the flow is gentle, but the medium is already present when a storm begins. A violent eruption does not cross a perfect vacuum toward an isolated planet. It moves through an existing sea of charged particles, overtaking slower streams, compressing magnetic fields, and building shock fronts as it travels. The quiet solar wind is therefore connected to the most extreme events. Both come from the same plasma ocean, and both reveal that the boundary of the Sun is not where visible light ends. Its matter, influence, and magnetism extend outward across millions of kilometers, linking the star to every world around it. The smooth disk in the sky is only the brightest layer of a much larger system. Beneath and beyond it, charged matter is always moving, and every movement has the power to become magnetic. Deep inside the Sun, motion becomes magnetism. The star does not contain a single buried magnet like a bar of iron hidden beneath its surface. Instead, its magnetic field is generated continuously by the movement of electrically charged plasma. This process is called the solar dynamo. In the Sun, the conductor is the plasma itself. The motion comes from rotation and convection, and the result is a vast field that changes shape, strength, and direction over time. The dynamo begins in a body that refuses to rotate as one solid object. Near the equator, the solar surface turns more quickly than regions close to the poles. Beneath the surface, different layers also rotate at different rates. Where these regions meet, plasma is sheared, stretched, and folded. Magnetic field lines carried within the plasma are pulled along with that motion. A field that once runs mainly from pole to pole can be drawn around the star until it becomes wrapped in long bands. The sun's rotation steadily winds magnetism through its interior, storing order inside turbulence and tension inside motion. Convection adds another layer of complexity. Hot plasma rises from deeper regions, cooler plasma sinks, and enormous circulating cells transport energy toward the surface. Because the sun rotates, these flows do not move in simple straight paths. They curve, twist, and interact across different latitudes. The result is not one smooth global field, but a complicated mixture of large patterns and smaller structures. Some magnetic fields remain buried for a time. Others rise toward the surface in buoyant loops, carrying concentrated magnetism into the photosphere. Where these loops break through, sunspots often appear. A pair of sunspots may mark the two ends of a magnetic arch, with one region carrying one magnetic polarity and the other carrying the opposite. They are visible signs that deep magnetic structures have reached the surface. The strength of the field suppresses some of the normal upward transport of heat, so the region becomes cooler and darker than its surroundings. Around it, however, the magnetic environment can be crowded with energy. Loops rise into the corona, plasma follows their shape, and active regions develop above the spots. The dynamo therefore connects the unseen interior to the visible signs of solar weather. It builds the field below, carries it upward, and allows the outer atmosphere to become charged with stored energy. Over many years, the entire pattern changes. The number of sunspots rises and falls in a cycle that averages about 11 years from one maximum to the next. Near solar minimum, the visible surface may remain almost free of spots for days or weeks. The global magnetic field is relatively simple, and activity is often lower. As the cycle advances, more sunspots emerge, active regions become frequent, and the magnetic field grows increasingly tangled. Near solar maximum, eruptions become more common, though powerful events can still occur outside the peak. Its length varies, its strength changes, and some cycles produce far more activity than others. The sun has entered periods in the past when sunspots become unusually rare for decades, and other periods show stronger magnetic behavior. Beneath the broad cycle lies an even longer magnetic rhythm. At each solar maximum, the sun's global magnetic poles reverse. North becomes south, and south becomes north. A complete return to the original orientation therefore takes roughly twice the sunspot cycle. The reversal does not happen as a clean, instant flip. The polar fields weaken, become disordered, and rebuild with opposite polarity. During this transition, the sun's magnetic structure can become especially complex. The large field stretches outward through the solar wind, forming a vast region called the heliosphere. As the sun rotates, the outward flowing field takes on a spiral shape, extending beyond the planets. The entire solar system sits within this magnetic influence. Earth moves through it continuously, encountering sectors where the field points in different directions and streams of solar wind move at different speeds. The dynamo is therefore not confined to the star. Its changing pattern is carried outward, giving interplanetary space a weather of its own. Yet the precise operation of the dynamo remains difficult to observe. The layers that create the field are hidden beneath the photosphere, and no instrument can descend into the solar interior. Scientists must infer the motion through surface measurements, oscillations, magnetic maps, and computer models. Heliosismology reveals that one important transition lies near the base of the convection zone, where the rotating outer region meets the more uniform interior. This boundary is called the tachocline. Strong shear in this region may help stretch and amplify magnetic fields. At the same time, near-surface convection and smaller turbulent flows also appear to play important roles. It may emerge from interactions across much of the solar interior, with large-scale circulation carrying magnetic flux between the equator and the poles, while turbulence continually reshapes it. Motion creates and reorganizes magnetic fields, but the details determine when and where energy becomes dangerous. A small difference in the flow may change the strength of a cycle. A change in the speed of circulation may delay the arrival of magnetic flux at the poles. A cluster of rising fields may form a simple active region, or a tightly mixed one in which opposite polarities press close together. The most magnetically complex regions often produce the strongest eruptions because they contain more stress and more opportunities for reconnection. Predicting the solar cycle is therefore not the same as predicting a particular storm. A forecast may estimate whether the coming years are likely to be active. Yet the exact timing of an eruption depends on local magnetic conditions that can change rapidly. The dynamo prepares the stage, but the final release belongs to the unstable structures above the surface. Even so, understanding the cycle matters greatly for civilization. Satellites experience more radiation and atmospheric drag during active periods. Radio communication can become less reliable. Astronauts beyond strong shielding face greater exposure to energetic particles. Power grid operators pay closer attention to geomagnetic forecasts when large active regions face Earth. Space agencies plan missions with the solar cycle in mind, especially when crews may travel beyond the protection of the lower atmosphere and magnetic field. The dynamo's slow rhythm therefore enters decisions made on and around Earth. An internal flow of plasma, hidden beneath a bright surface, can influence the design of spacecraft, the timing of launches, and the operation of electrical systems millions of kilometers away. Its presence is known through effects. Plasma traces its loops. Sunspots mark its emergence. Polar reversals reveal its global change. Auroras show how its disturbances interact with Earth. Instruments measure its direction and strength, turning invisible structure into maps. These maps often show a solar surface divided into patches of positive and negative polarity, with lines of force joining one region to another. During quiet times, the pattern may be broad and orderly. During active times, it becomes dense and fragmented. The appearance resembles a star covered not in isolated spots but in competing magnetic territories, each connected through the atmosphere by fields that may stretch far beyond the visible disk. Energy accumulates because the footpoints of these fields are anchored in moving plasma. Convection drags them, rotation shears them. New magnetic flux rises beneath existing structures. The corona is forced to adjust, but it cannot always do so smoothly. Some loops expand, some reconnect in minor events. Others hold their shape while tension grows. The dynamo never decides to create a storm. It simply continues its cycle of motion and field generation. Yet within that cycle, the possibility of eruption is built into the system. The sun's magnetism is not a decoration surrounding the deeper process of fusion. It is a second architecture laid across the star, an invisible framework that channels plasma, heats the corona, drives the solar wind, and stores the energy released in the most powerful explosions. Gravity holds the sun together, fusion supplies its light, and the dynamo gives its outer layers their changing, restless character. Without the dynamo, the sun might still shine, but the space around it would be far quieter. With it, the star becomes a source of cycles, storms, and long-reaching magnetic influence. Every sunspot is a small opening into that hidden machinery. Every reversal shows that the machinery never stops, and every quiet interval carries the same unresolved tension, because the field is still being stretched beneath the surface, preparing new structures whose final shape cannot yet be known. Above the visible surface of the sun, magnetic fields rise in arches, loops, and tangled structures that can hold plasma high in the corona. These formations may appear graceful and almost still, but their stillness is temporary. The footpoints of each loop remain rooted in the moving photosphere, where convection carries plasma sideways and differential rotation drags one region past another. As those anchored points shift, the magnetic field is twisted. Lines that once followed simple curves begin to shear against neighboring lines. New magnetic flux can rise beneath older structures, forcing them upward or pressing fields of opposite direction into close contact. The corona gradually becomes a place of stored tension. Energy is added not by one sudden act but by countless motions below, each small compared with the scale of the star, yet persistent enough to change the shape of the field. Magnetic fields resist being bent. They exert tension along their length and pressure across the space they occupy. In the solar atmosphere, these forces compete with gravity, gas pressure, and the motion of plasma. A loop can remain suspended because the magnetic field supports the material trapped along it. A prominence, which is a cooler and denser ribbon of plasma, may hang above the surface for days or even weeks inside a magnetic cradle. From Earth it can seem delicate, but the structure may stretch across distances larger than the planet. Its apparent calm hides a balance that depends on the surrounding field maintaining the right form. As the photosphere continues to move, that balance can weaken. The field becomes more twisted, the current within it grows, and the structure approaches a threshold that is difficult to see from outside. The danger lies in the way magnetic systems can change state. A slowly stressed field does not always release its energy slowly. For a time, it may adjust through small movements, minor heating, or weak bursts. Then a critical arrangement develops. Oppositely directed field lines are brought together in a narrow region. The usual connection between plasma and field begins to break down at very small scales. The field lines change partners, joining in a new pattern. This process is called magnetic reconnection. It is one of the central mechanisms behind explosive solar activity. Reconnection does not destroy magnetism. It rearranges the field into a lower energy form, and the difference is released into the surrounding plasma. Some of that energy becomes heat, some becomes motion, some accelerates charged particles to high speeds, some emerges as radiation across the electromagnetic spectrum. A structure that has stored energy over many hours or days can transform within minutes. There may be many interacting loops, multiple reconnection sites, and waves moving through the corona as the field reorganizes. The eruption can spread from one region to another. Triggering further changes, a bright flare may appear near the surface while a much larger magnetic structure begins to rise above it. Plasma that had been confined is heated and thrown outward. Nearby loops may collapse into a new shape. Radio emissions may signal energetic electrons escaping along open field lines. X-rays may brighten as hot plasma fills newly formed loops. What appears as one event is often a chain of connected changes unfolding across a vast active region. Not every twisted field erupts. Some structures unwind gradually or lose energy through smaller events. Some active regions cross the visible face of the sun without producing a major storm. Others release repeated flares before becoming quiet. This uncertainty is one of the hardest parts of solar forecasting. Scientists can measure magnetic complexity, track the growth of sunspots, observe rising filaments, and identify patterns associated with instability. They can see when a magnetic polarities are tightly packed, or when a loop system is becoming strongly sheared, yet the exact moment of release remains difficult to predict. The corona contains three-dimensional structures that cannot be fully measured from a single viewpoint, and the most important changes may occur in regions hidden above or beneath the visible surface. A field may look stable until it is not. When a large structure loses equilibrium, it can begin to rise. At first the movement may be slow. The magnetic field above it acts like a restraining cage, holding the structure down. Continued reconnection below the rising plasma can cut and rejoin field lines, adding upward force and forming a long current sheet beneath the eruption. Once the upward motion becomes strong enough, the structure accelerates. The restraining field is stretched outward, and more reconnection follows. This feedback can turn a quiet prominence into the core of a coronal mass ejection. Billions of tons of plasma may be lifted away from the sun, carrying an enormous magnetic field into interplanetary space. The eruption expands as it travels, becoming a vast cloud whose size may eventually exceed the distance between Earth and the Moon. The flare and the ejection are often linked, but they are not the same object. The flare is a rapid release of energy seen mainly as radiation and heated plasma near the sun. The coronal mass ejection is the outward-moving magnetic cloud and material. A powerful flare can occur without a large ejection, and an ejection can sometimes leave the sun with only a modest flare. Their connection depends on the geometry of the field and on whether the eruption remains confined or escapes into space. In a confined event, overlying magnetic fields hold the disturbance near the surface. In an eruptive event, the structure breaks through. This distinction matters for Earth. Radiation from a flare may disrupt the upper atmosphere and radio communication almost immediately on the sunlit side of the planet. While an ejection may take many hours or several days to arrive, the first flash reveals that magnetic energy has been released, but it does not by itself determine how severe the later geomagnetic effects will be. Direction is critical. The sun launches material into a wide range of paths. Some eruptions move far above or below the plane of Earth's orbit. Some appear near the edge of the solar disk and travel sideways from Earth. Others begin near the center of the visible face and expand outward in a way that suggests a direct approach. Even then, the structure may pass mostly to one side. Yet the most dangerous events do not need perfect aim. A broad, fast ejection can sweep across a wide region of interplanetary space, driving a shock ahead of it. If that shock and the magnetic cloud behind it cross Earth's orbit, the planet enters the disturbed environment created by the eruption. Speed adds another layer of danger. A slow ejection may merge gently into the ordinary solar wind. A fast one compresses the plasma and magnetic field ahead of it, forming a shock capable of accelerating particles. If several eruptions leave the sun in succession, a later and faster ejection can catch an earlier one. The resulting interaction may strengthen the disturbance, alter its magnetic structure, or clear a path through the solar wind that allows the later cloud to travel more quickly. The event that reaches Earth is therefore shaped not only by its birth near the sun, but by everything it encounters on the journey. The original magnetic knot continues to change as it expands across space. The source of the danger remains the same energy stored in stressed magnetic fields. Fusion provides the sun's immense power, but magnetic structure determines when part of that power is released suddenly into the corona. The eruption is not a random explosion without preparation. It is the final stage of a long sequence. Plasma moves, field lines are carried and twisted, electric currents grow, magnetic pressure builds. A stable arrangement becomes less stable. Reconnection begins, and the entire system seeks a new configuration. In that transition, the sun converts invisible tension into visible light. Heat, radiation, and motion. The scale can be difficult to hold in mind. A loop that looks thin through a telescope may contain enough energy to affect technology across an entire planet. A brightening that lasts only minutes may announce a cloud that will travel for millions of kilometers. A silent change in the corona may send particles outward at speeds no material object on Earth can approach. Yet even the largest solar eruption is still part of the star's ordinary magnetic life. The sun is not becoming unnatural when it flares. It is releasing the strain created by its own rotation and convection. The mystery is not why such events happen, but why one active region remains quiet while another breaks. Why one ejection misses Earth while another arrives directly, and why one magnetic cloud passes with little effect while another opens a path into the planet's defenses. The knots form gradually, but the consequences depend on how they come undone. A solar eruption does not arrive as one single thing. It can unfold as light, particles, and moving plasma, each leaving the sun by a different route and reaching Earth on a different timescale. The first signal may be a sudden flare, a brilliant release of electromagnetic radiation produced when magnetic energy is converted into heat and particle motion. Visible light may increase only slightly, while ultraviolet radiation and X-rays can rise dramatically. Because this radiation travels at the speed of light, it crosses the distance from the Sun to Earth in a little more than 8 minutes. By the time instruments detect the burst, the radiation has already reached the upper atmosphere. Most people at the surface remain protected, but the ionosphere can change almost immediately. A strong flare can increase ionization on the sunlit side of Earth and cause shortwave radio blackouts. Communication used by aircraft, ships, emergency services, and remote regions may become unreliable. Navigation signals can also be disturbed because they must pass through the changing ionosphere before reaching receivers below. The flare is fast and nearly instantaneous in its effects, but it is only one part of the storm. At the same time, the eruption may accelerate protons and other atomic nuclei to enormous energies. These particles can escape along magnetic field lines and race through the solar system. They do not move at the speed of light, but the fastest can arrive near Earth within tens of minutes. This creates a solar radiation storm, sometimes called a solar proton event. The danger is greatest above the protection of the lower atmosphere. Satellites may experience electrical charging, damaged electronics, corrupted data, and degraded solar panels. Astronauts can receive increased radiation exposure, especially outside a heavily shielded spacecraft or beyond the strongest protection of Earth's magnetic field. Aircraft flying high polar routes may also face increased exposure because magnetic field lines guide energetic particles toward the poles. A sufficiently energetic proton can pass through material and deposit energy along its path. In electronics, this may flip a stored bit or damage a sensitive component. In cells, it can disturb molecules and break chemical bonds. The atmosphere absorbs most of this radiation before it reaches the ground, which is why solar proton storms are not usually direct health emergencies at sea level. Their seriousness belongs mainly to systems operating in near space and at high altitude. The third major part of an eruption is slower but often far larger. A coronal mass ejection is a vast cloud of plasma and magnetic field thrown outward from the corona. It may contain millions or billions of tons of solar material. The cloud begins near the sun as an expanding magnetic structure, then grows wider as it moves into space. Some ejections travel only a few hundred kilometers each second. The fastest can exceed 2,000 kilometers each second and reach Earth in less than a day. Others take several days. Their arrival time depends not only on their original speed but on the solar wind through which they move. A fast cloud may slow as it pushes into slower material. A shock wave often forms ahead of a fast ejection. This shock compresses plasma and magnetic fields in the solar wind, and it can accelerate additional particles. Earth may therefore encounter disturbed conditions before the main magnetic cloud arrives. Instruments in space can detect changes in speed, density, temperature, and field direction as the structure approaches. The sequence may begin with the shock, followed by a turbulent sheath of compressed plasma, and then the more organized magnetic cloud itself. Each region can affect Earth differently. The shock can jolt the magnetosphere. The sheath can produce rapidly changing magnetic conditions. The cloud may contain a long interval of magnetic field pointing in a direction that connects strongly with Earth's field. That final orientation is often decisive. A large fast ejection can pass with limited consequences if its magnetic field is poorly aligned for transferring energy into the magnetosphere. A smaller event can produce a stronger geomagnetic storm if its field remains directed in the more dangerous orientation for many hours. Size and speed matter, but geometry determines how deeply the disturbance enters Earth's magnetic system. Flares, proton storms, and coronal mass ejections are often discussed together because they can emerge from the same active region, yet they are not interchangeable. A flare is radiation. A proton storm is a stream of energetic particles. A coronal mass ejection is a moving structure of plasma and magnetic field. They travel differently, arrive at different times, and threaten different systems. The flare may affect radio communication almost at once. Energetic particles may follow soon afterward and increase radiation risk. The coronal mass ejection may arrive much later and disturb the magnetic environment around the entire planet. One eruption can therefore create several waves of danger, separated by minutes, hours, or days. This layered timing gives space weather forecasters both a problem and an opportunity. The fastest effects arrive with almost no warning, but the slower cloud may be observed as it leaves the sun. Coronagraphs block the bright solar disk and reveal the faint corona around it, allowing an expanding ejection to be tracked. Other instruments measure the flare, map the source region, and detect energetic particles. From these observations, scientists estimate the cloud's direction and speed. The estimate is never perfect because the eruption expands in 3 dimensions, while most observations view it from limited angles. A cloud moving directly toward Earth may appear as a faint halo spreading around the hidden sun, making its true speed difficult to judge. Its internal magnetic orientation is even harder to know at a distance. The most important measurement often comes from spacecraft positioned between Earth and the Sun. These craft sample the solar wind before it reaches the planet. They can detect the magnetic field carried by the approaching cloud and reveal whether it is likely to connect strongly with Earth's field. Yet their location provides only a short final warning, often measured in tens of minutes. By then, the eruption has crossed almost the entire distance between the Sun and Earth. The layered nature of solar storms also explains why dramatic images do not always match dramatic consequences. A brilliant flare can attract attention while sending little plasma toward Earth. A faint eruption from a favorable location may launch a broad cloud directly across the planet's orbit. A strong proton event may threaten spacecraft without causing a major geomagnetic storm. An intense geomagnetic storm may follow an ejection whose visible flare was not among the largest. The danger cannot be judged from brightness alone. It must be understood as a combination of radiation, particles, a plasma, magnetic direction, and timing. The sun always emits radiation, including the visible light that warms Earth. During a flare, the concern is not that radiation suddenly begins, but that certain high-energy wavelengths increase sharply. X-rays and extreme ultraviolet radiation are absorbed high in the atmosphere. They do not burn cities or pass freely through buildings, but they can transform the ionosphere and heat the upper atmosphere. That heating makes the atmosphere expand outward, increasing drag on satellites in low orbit. Spacecraft may lose altitude more quickly, and operators may need to adjust their paths. Thus, even radiation that never reaches the ground can influence systems through changes where satellites travel. Civilization has placed essential machines directly inside this environment. Communication, weather monitoring, navigation, scientific observation, and timing systems all depend on spacecraft operating above most of the atmosphere. Solar activity reaches those systems before it reaches any wire on the ground. Beyond that shell, the risk grows still greater. Crews travelling toward the Moon or Mars cannot rely on the same protection available in low Earth orbit. A major proton event could deliver a dangerous dose during a spacewalk or inside a lightly shielded vehicle. Future exploration therefore depends on storm shelters, radiation monitoring, forecasting, and mission plans that recognize the Sun as an active environment rather than a distant light. The three forms of eruption reveal three faces of the same magnetic release. Light moves first, particles follow. Plasma carries the deepest magnetic disturbance behind them. The sequence may pass almost unnoticed, or it may build toward a storm that reaches from the upper atmosphere to the power systems below. Nothing in the visible calm of the Sun announces which outcome will follow. Only instruments can separate the signals and measure the approaching layers. The hidden danger is not a single blow, but a procession, with each part moving at its own speed and testing a different weakness in the systems round Earth. Earth does not meet the solar wind as an exposed world. Long before charged particles can reach the ground, they encountered two vast protective systems, the atmosphere and the magnetic field. Together they absorb, deflect, slow, and redirect much of the energy arriving from the Sun. These defences are not perfect walls, and they do not stop every effect, but they transform a hostile stream of radiation and plasma into conditions under which life and civilization can exist. The first shield is the atmosphere. It is thin compared with the size of the planet, yet it contains enough matter to absorb most dangerous solar radiation before it reaches the surface. X-rays and extreme ultraviolet light are stopped high above the ground, where they ionize atoms and molecules in the upper atmosphere. This is why strong solar flares can disturb radio communication without directly burning people below. The energy is deposited far overhead, while the surface remains largely protected. Visible light passes through while more damaging wavelengths are filtered by the layers above. The second shield is less tangible. Earth's magnetic field extends far beyond the atmosphere into space, forming a region called the magnetosphere. It is generated by motion in the planet's liquid outer core, where electrically conducting iron circulates and creates a global field. Farther out, the solar wind distorts it. On the side facing the Sun, the field is compressed. On the night side, it is stretched into a long tail that reaches far beyond Earth. The magnetosphere therefore has no simple spherical shape. It is a changing cavity carved out of the solar wind, always adjusting to pressure from the star. Most charged particles cannot cross directly through this field. Their paths bend as they enter the magnetic environment, and many are diverted around the planet. Some become trapped in radiation belts. Others are guided toward the polar regions, where magnetic field lines connect more directly with the upper atmosphere. This guidance produces one of the most beautiful signs of space weather. When energetic electrons and ions collide with oxygen and nitrogen high above Earth, they transfer energy to those atoms and molecules. The excited particles then release light, green, red, blue, and violet glows spread across the sky as auroras. What appears from the ground as a quiet curtain of light is the visible result of charged matter entering the atmosphere along magnetic pathways. Auroras are therefore both spectacle and evidence. They show that the protective field does not simply block the solar wind. It channels part of the incoming energy into limited regions and allows the atmosphere to absorb it. During ordinary conditions, auroras remain concentrated near the poles. During stronger disturbances, they expand toward lower latitudes because the magnetosphere is compressed and energized. The auroral zones move, brighten, and develop rapidly changing forms as currents flow through near-Earth space. The magnetosphere, ionosphere, and ground form a connected electrical system. This connection becomes especially important during geomagnetic storms, but even in quiet periods it is always present. Earth's protection is dynamic because the solar wind is dynamic. The magnetosphere responds by changing size and shape. When solar wind pressure increases, the dayside boundary moves inward or outward, while the tail stretches and relaxes. Magnetic energy enters, is stored, and is released. The planet's field behaves less like rigid armor and more like a flexible shield that bends under impact. This flexibility prevents much of the incoming plasma from reaching the atmosphere directly, but it also creates pathways through which energy can enter. The most important pathway appears when the magnetic field carried by the solar wind points in the opposite direction to Earth's field on the day side. Under that arrangement, the two fields can reconnect. Solar wind energy then crosses into the magnetosphere more efficiently. The same process that releases energy near the Sun can open Earth's magnetic boundary without removing the shield. Magnetic flux is pulled across the poles and carried into the tail, where energy accumulates. Eventually, more reconnection can occur in the distant tail, sending particles and energy back toward Earth. This cycle drives auroral displays and contributes to geomagnetic storms. Under normal conditions, it is part of the planet's response to the solar wind. Under extreme conditions, it can become powerful enough to disturb technology across wide regions. The atmosphere stops high-energy photons and many particles by forcing them to collide with matter. The magnetic field acts earlier, changing the paths of charged particles before they reach dense air. Neither one is sufficient by itself in every situation. A planet with an atmosphere but little magnetic protection may still shield its surface from many forms of radiation. Yet its upper atmosphere can be exposed more directly to the solar wind. A planet with a magnetic field but a thin atmosphere may divert many charged particles while remaining vulnerable to other kinds of radiation. Earth benefits from both systems working together. Their combined protection is one reason the surface remains habitable beneath an active star. It also creates a deceptive sense of security, because people at ground level rarely feel solar storms directly. The danger seems remote. The atmosphere and magnetic field absorb the immediate physical assault so effectively that the event can pass unnoticed without instruments. Yet the same energy that is harmless to flesh and bone can still affect machines. Satellites orbit above much of the atmosphere, where shielding is weaker. Radio signals travel through the ionosphere, which solar radiation can disturb. Navigation systems depend on precise timing and on signals crossing regions whose electrical properties change during storms. Power grids extend across the ground as long conductors, vulnerable not to direct particle impact, but to slow changes in Earth's magnetic environment. The shields protect biology, while leaving technology exposed through other pathways. This distinction is central to the hidden danger. A severe solar storm is unlikely to strike the surface like a wave of fire. It threatens civilization through systems that reach into space or connect across great distances. The protective field can even help create those effects. When it is compressed, stretched, and reconnected, currents flow through the magnetosphere and ionosphere. Those currents produce changing magnetic fields at the ground. A changing magnetic field can induce electric currents in conductors, pipelines, communication cables, railway systems, and high-voltage transmission lines can all respond. The magnetosphere has absorbed and redirected the storm, but part of the energy is translated into a form that modern infrastructure can receive. Protection and vulnerability therefore exist within the same process. Even the atmosphere changes in ways that matter. During strong solar activity, ultraviolet and X-ray heating causes the upper atmosphere to expand. Satellites in low orbit encounter more drag and may lose altitude. A storm that remains invisible at the ground can alter thousands of objects moving overhead. At higher altitudes, energetic particles can charge spacecraft surfaces and penetrate electronics. The magnetosphere reduces exposure but cannot eliminate it, especially in regions where particles become trapped or funnel toward the poles. The shield has weak points, moving boundaries, and internal reservoirs of radiation. It is a living system in the physical sense, always exchanging energy with the sun. Most of the time, that exchange remains balanced. The solar wind flows past, the field bends, particles create faint auroras, and the atmosphere absorbs radiation without consequence below. This ordinary success makes the defences seem absolute. They are not. Their purpose is not to preserve technology, and they did not evolve to protect electrical networks, satellites, or digital communication. They arise from planetary physics. Life develops beneath them, and civilization later builds systems that depend on the quiet conditions they usually maintain. The danger appears when an unusually strong eruption forces the protective layers into an unusually disturbed state. The shields still prevent the worst direct effects from reaching the surface, but the energy finds indirect routes through magnetic coupling, atmospheric change, and induced current. Earth remains safe as a place for living bodies, yet the structures built by those bodies may begin to fail. The beauty of an expanding aurora can therefore carry a deeper meaning. It is the glow of a shield under pressure, a visible trace of energy that has crossed from the sun into the near-Earth environment. Most displays fade without harm. In a larger storm, the same pathways can widen, the same currents can strengthen, and the same invisible field that protects the planet can become the medium through which distant solar violence reaches civilization. A coronal mass ejection can cross the space between the Sun and Earth as an enormous cloud of plasma wrapped in its own magnetic field, but its arrival alone does not determine the severity of the storm that follows. The decisive factor is often the direction carried inside that cloud. Earth's magnetic field points outward in one broad orientation on the sunward side of the planet, while the incoming solar field may point in many possible directions. When the two fields are arranged so that they oppose one another, their lines can reconnect. This connection allows solar wind energy to cross the boundary of the magnetosphere far more efficiently. The shield does not disappear, yet its outer surface becomes open to a deeper exchange. Magnetic flux is peeled away from the dayside, swept over the poles, and dragged into the long tail behind Earth. The process begins quietly in invisible fields, but it can reorganize the entire magnetic environment around the planet. A fast ejection usually announces itself first through a shock. The shock compresses the solar wind and strikes the magnetosphere, forcing the dayside boundary closer to Earth. Satellites that normally remain well inside the protected region may suddenly find themselves nearer its edge or briefly exposed to disturbed solar plasma. Instruments register a rapid change in magnetic strength. Currents begin to intensify in the ionosphere and around the planet. This first compression is sometimes only the beginning. Behind the shock lies the turbulent sheath, a region of squeezed and irregular plasma where the magnetic field can change direction rapidly. After that may come the more organized magnetic cloud, often rotating gradually as it passes. If a long part of the field points in the unfavorable direction, reconnection continues for hours, and the magnetosphere absorbs energy faster than it can release it gently. The transferred energy is carried into the magnetotail. On the night side of Earth, magnetic field lines are stretched into two broad lobes separated by a sheet of electrical current. As more solar magnetic flux is added, the tail lengthens and stores energy. The structure resembles a system under growing tension, though the true geometry is far more complex than any simple elastic band. Eventually, reconnection begins within the tail. Field lines that have been stretched far from Earth break and join in new arrangements, some close into loops that are carried away down the tail. Others snap back toward the planet, accelerating plasma and sending bursts of particles inward. The stored energy is released in a sequence of disturbances called substorms. Auroras brighten and move, currents intensify. The night side of the magnetosphere becomes a region of sudden motion after a long period of loading. A geomagnetic storm is broader and longer lasting than a single substorm. It develops when sustained solar wind conditions inject large amounts of energy into the near-Earth environment. One important result is the strengthening of a vast electrical current that circles the planet, carried by charged particles trapped in the inner magnetosphere. As this ring current grows, it produces a magnetic field that partly opposes Earth's own field at the surface. Ground observatories detect the resulting decrease in magnetic strength. The storm is therefore measured not by visible damage alone, but by the degree to which the entire magnetic system has been altered. Auroras expand toward lower latitudes because the regions of strongest particle precipitation move away from the poles. In extreme events, lights normally confined to high northern and southern skies can appear over places that rarely see them. Their beauty is produced by the same energy transfer that drives less visible hazards. Electrons pour into the upper atmosphere, colliding with oxygen and nitrogen and causing them to glow. At the same time, powerful currents flow along magnetic field lines between space and the ionosphere. Other currents spread horizontally through the upper atmosphere. Together they create magnetic variations that can be detected across continents. The faster and larger those variations become, the greater the possibility of induced currents in long conductors on the ground. The orientation of the incoming field is so important because magnetic reconnection depends on opposition. If the solar field points in a direction similar to Earth's field at the dayside boundary, the two systems do not connect as efficiently. The magnetosphere may still be compressed, satellites may still experience disturbed conditions, and energetic particles may still arrive, but the deepest transfer of energy is reduced. If the solar field turns and remains oppositely directed, the boundary becomes far more active. The same ejection can therefore produce different consequences depending on which part of its internal magnetic structure reaches Earth. A cloud may begin with a harmless orientation, then rotate into a dangerous one. Forecasts may improve only shortly before arrival, when spacecraft positioned upstream directly measure the field. This creates an uncomfortable limit. Telescopes can see an ejection leave the Sun many hours or days earlier. Models can estimate its speed and likely path, yet the magnetic direction inside the cloud is difficult to determine from remote observations. The strongest clue may not arrive until the storm is almost at Earth. Spacecraft stationed near a gravitational balance point between the Sun and Earth sample the approaching solar wind before it reaches the magnetosphere. Their measurements reveal the density, speed, temperature, and magnetic orientation of the plasma. When the field turns into the dangerous direction and stays there, Forecasters know that strong coupling is likely. The warning may then be measured in less than an hour. That period can still be valuable, but it is narrow compared with the scale of the event. Grid operators may adjust transmission patterns, satellite controllers may place spacecraft in safer configurations, and aviation authorities may reconsider polar routes. The final forecast is therefore not a prediction made from certainty, but a rapid response to conditions measured just upstream. The storm itself does not strike the entire planet in a uniform way. Local geology influences how electrical currents move through the ground. Regions with resistant rock can force currents into power lines and pipelines more strongly than regions where the ground conducts electricity more easily. The shape and direction of transmission networks also matter. Long lines running across certain orientations may collect larger induced voltages, time of day, latitude, storm phase, and the changing position of ionospheric currents all affect the result. One transformer may experience little stress while another hundreds of kilometers away receives a damaging current. The magnetic storm is global, but its technological consequences emerge through local paths. Satellites face a different pattern of risk. The compressed magnetosphere can expose high-orbit spacecraft to conditions they do not normally encounter. Energetic particles can penetrate shielding, charge surfaces, and build electrical differences between spacecraft components. A sudden discharge may disrupt electronics. Increased radiation can create errors in computers or degrade detectors and solar panels. The upper atmosphere also heats and expands, increasing drag on satellites in lower orbits. Orbits become harder to predict, and spacecraft lose altitude more quickly. The same storm that drives currents through systems on the ground changes the environment of machines thousands of kilometers above it. Navigation signals pass through an ionosphere filled with irregularities. Their paths bend, their timing shifts, and receivers may calculate positions less accurately. High-frequency radio waves may be absorbed or reflected unpredictably. A geomagnetic storm therefore reaches civilization through several connected layers, from the magnetosphere to the atmosphere, from the atmosphere to orbit, and from changing magnetic fields into wires on the surface. Nothing in this process requires solar plasma to descend into cities. The danger travels through coupling. Energy begins in twisted fields above the sun, crosses interplanetary space inside an expanding cloud, enters Earth's magnetosphere through reconnection, accumulates in the tail and ring current, and finally appears as radiation, atmospheric disturbance, auroral current, and induced electricity. Each stage transforms the original eruption without erasing its influence. By the time lights flicker or a satellite enters safe mode, the solar material itself may still be far above the atmosphere. What reaches the machine is a consequence carried through fields. This is why alignment matters more than appearance. A vast eruption can seem terrifying in images, yet pass with limited effect if its magnetic field turns the wrong way for strong coupling. Another event may appear less dramatic but carry a sustained opposing field that opens the magnetosphere for hours. The hidden danger is written inside the cloud, in a direction that cannot be seen by the eye. Earth's defenses remain powerful, but they are not closed. Under the right alignment, the magnetic field of the planet and the magnetic field of the sun become temporarily linked. An energy stored millions of kilometers away begins to move through the invisible architecture surrounding civilization. Modern civilization rests on an electrical network so widespread that it is almost invisible. Power lines cross open land, cables run beneath streets and oceans, transformers stand behind fences, and substations quietly regulate the movement of energy from generators to homes, hospitals, factories, data centers, and communication systems. Under ordinary conditions, this network behaves with remarkable precision. Alternating current changes direction many times each second. Voltage is raised for long-distance transmission and lowered again for local use, and protective devices isolate faults before they spread. Yet the same scale that makes the grid efficient also creates a weakness during a geomagnetic storm. Long conductors can collect electric currents induced by slow changes in Earth's magnetic field, and those currents do not behave like the electricity the grid is designed to carry. They enter through grounded connections, move through transmission lines, and pass into transformers as an unwanted direct current. The process begins far above the ground, but its effects appear inside machines built from steel, copper, oil, insulation, and carefully balanced magnetic fields. A transformer works by transferring energy between coils through a changing magnetic field in an iron core. In normal operation, the alternating current produces a magnetic cycle that remains within safe limits. A geomagnetically induced current shifts the balance. It pushes the core toward magnetic saturation during part of each cycle, meaning the iron can no longer respond in the expected linear way. When saturation occurs, the transformer draws additional reactive power, heats unevenly, produces harmonics, and places stress on other parts of the network. Protection systems may misread the disturbance. Voltage can become unstable. Equipment can vibrate, overheat, or fail. The dangerous current may be small compared with the normal power flowing through a line. Yet because it enters in the wrong form and persists across wide areas, it can disturb many components at once. This is what makes a severe geomagnetic storm different from a local electrical fault, a lightning strike, fallen tree, or equipment failure begins at a specific point. Operators can often isolate the damaged section and route power around it. A solar storm can affect transmission systems across entire regions at nearly the same time. It does not need to destroy every transformer to create a crisis. If enough major components become overloaded, protective systems may disconnect lines, generation may fall out of balance with demand, and instability can spread through the grid. Sections can separate from one another. Voltage can collapse. A disturbance that begins as an invisible current may end as a blackout covering cities and provinces. The grid is built as a connected system, and connection allows both strength and vulnerability. Electricity can be shared across large distances, but trouble can also travel. Long high-voltage lines are especially exposed because they span great distances and often connect to the ground through transformer neutrals. The amount of induced current depends on how rapidly the magnetic field changes, how conductive the ground is, how the lines are oriented, and how the network is configured at that moment. Certain geological regions can intensify the effect. Resistant bedrock does not allow current to move easily through the earth, so more of the induced flow may enter artificial conductors. Coastal boundaries can also complicate the pattern, because seawater and continental rock conduct electricity very differently. The same geomagnetic storm can therefore produce unequal stress across neighbouring areas. One country may see modest disturbances while another experiences dangerous currents in key transformers. Maps of risk depend not only on latitude but on geology, infrastructure, and grid design. The danger extends beyond power transmission. Pipelines can collect induced currents that interfere with corrosion protection systems. Railway signalling circuits may experience false indications. Long communication cables can carry unexpected voltages, especially where grounded repeaters or power feeding systems create conductive paths. Undersea cables are largely protected from the direct action of magnetic storms because seawater reduces rapid field changes. Yet their power systems and landing infrastructure may still require careful design. Satellites face a separate set of threats. Radiation can alter electronics, while geomagnetic disturbances change the density of the upper atmosphere and increase drag. Communication spacecraft may enter protective modes. Navigation signals may become less accurate. Weather satellites can experience data interruptions. A civilization that depends on precise timing and continuous communication is therefore vulnerable through many link systems at once. Electrical power sits near the center of those links. Without stable electricity, mobile networks rely on batteries and generators. Data centers switch to backup systems. Water pumps, fuel distribution, traffic control, refrigeration, and medical equipment begin operating under emergency limits. The immediate failure may be magnetic, but the wider consequences become logistical. The most difficult components to replace are often large power transformers. These machines are custom-built, heavy, expensive, and slow to manufacture. Some weigh hundreds of tons and require special transport routes. They are not stored in unlimited numbers because each grid uses different designs and voltage classes. Severe internal damage can therefore create a recovery problem much larger than the initial outage. A temporary storm may last hours, while the repair of major equipment may take months. The true risk depends on how many transformers are damaged rather than merely disturbed. Most geomagnetic events cause manageable effects. Operators can reduce loading, adjust generation, and monitor currents. Protective systems may trip without permanent harm. A worst-case scenario requires several conditions to align a strong and sustained geomagnetic disturbance: vulnerable network geometry, heavy system loading, insufficient preparation, and equipment operating near its limits. The uncertainty is significant. Transformers differ in age, construction, and tolerance. Some studies predict widespread but mainly temporary disruption, while others warn that a severe storm could damage enough critical units to prolong recovery. The disagreement does not mean the risk is imaginary. It reflects the difficulty of modelling a continental network under rare conditions that cannot be tested safely at full scale. Evidence comes from past storms, laboratory work, engineering models, and measurements taken during smaller events. One clear warning arrives in March of 1989, when a geomagnetic storm causes the power grid in Quebec to collapse within about a minute and a half. The blackout lasts for hours and affects millions of people. The event does not destroy civilization, but it demonstrates how quickly space weather can enter an electrical network. Protective relays respond to abnormal conditions, key lines trip, and the system loses stability. Other utilities in North America observe transformer heating and unusual power flows. The storm becomes a practical lesson: the sun can reach the grid without touching the ground. Modern operators now use better monitoring, forecasting, and procedures, but the network has also become more complex and more essential. Electricity supports systems that did not exist during earlier storms. Digital finance, cloud computing, satellite navigation, automated logistics, and global communication all assume that power and timing remain available. Even brief disturbances can have economic effects far beyond the affected lines. A larger event could create simultaneous problems in orbit, in the ionosphere, and across the grid, making diagnosis and coordination more difficult. During an ordinary blackout, communication helps crews locate faults and restore service. During a solar storm, the systems used for coordination may themselves be degraded. Navigation may be less reliable. Radio channels may be disturbed, and satellite links may be interrupted. The event challenges not only hardware but situational awareness, yet the grid is not defenseless. Operators can measure geomagnetically induced currents, compare them with models, and change network conditions to reduce stress, power can be rerouted, vulnerable equipment can be taken out of service, reactive power reserves can be increased. Maintenance schedules can consider space weather risk, transformers can be designed with greater tolerance, and blocking devices can limit direct current entering certain parts of the network. These protections require planning because they cannot be invented after the storm has already arrived. The hidden danger lies in the mismatch between the age of the sun and the age of the grid. Solar eruptions have crossed Earth's orbit for billions of years. High-voltage transmission networks have existed for only a small fraction of that time. The star has not become more hostile. Civilization has built long conductors, sensitive electronics, and tightly connected systems beneath its changing magnetic influence. The vulnerability is therefore partly self-created, not through carelessness, but through dependence. The wires that carry energy across a continent also offer a path for currents induced by a storm in space. Most days, that path remains quiet during the wrong magnetic alignment. It can become the route by which the sun enters the machinery of civilization. History records solar storms indirectly, through the reactions of skies, instruments, wires, and machines. Before the electrical age, a powerful geomagnetic disturbance may pass over Earth as an unusual aurora, a compass deviation, or a glow seen far from the poles. The event leaves no burned landscape and no crater. Its energy is distributed through the magnetic environment of the planet, and unless observers understand what they are seeing, the evidence can fade into memory. This makes the 19th century a turning point. By then, telegraph networks stretch across continents, observatories measure the magnetic field, and astronomy begins to watch the sun with enough precision to connect a solar eruption with events on Earth. The strongest example arrives in late August and early September of 1859. It becomes known as the Carrington Event, named after the British astronomer Richard Carrington, who observes an extraordinary flash in a sunspot group. At that moment, he's not watching a smooth and featureless sun. He's tracing the changing shape of dark spots projected through a telescope, a safer method than looking directly at the solar disk. A brilliant patch suddenly appears over the active region. It intensifies, changes form, and fades within minutes. Another observer, Richard Hodgson, sees the same event independently. The flash is later understood as a white light solar flare, a rare eruption bright enough to be detected against the visible surface. Its significance becomes clear when Earth's magnetic field begins to react. Magnetometers record a rapid disturbance around the time of the flare, probably caused by radiation reaching the upper atmosphere. Then, less than a day later, a much larger geomagnetic storm begins. The short travel time suggests that an exceptionally fast coronal mass ejection crosses the distance from the Sun to Earth. It may also move through space already disturbed by an earlier eruption, allowing the later cloud to travel with less resistance. The exact sequence cannot be reconstructed with modern precision, but the effects are unmistakable. Auroras spread far beyond their usual latitudes. Reports describe red, green, and white light across skies where such displays are rare. In parts of the Caribbean, observers see auroral glows. In North America and Europe, the night becomes bright enough in some places for people to mistake the light for dawn. The atmosphere is not burning, and the sun has not risen early. Energetic particles are entering the upper air, and powerful currents are flowing through the planet's magnetic system. The visual spectacle is only the most visible part of the storm. The telegraph network reveals the electrical consequences. Telegraph systems operate through long wires, batteries, switches, and electromagnetic receivers. They are simple compared with a modern power grid, but their long conductors make them sensitive to changing magnetic fields. During the storm, Induced currents enter the lines. Some operators receive electric shocks. Equipment throws sparks. Telegraph paper catches fire in a few offices. Signals become distorted or unusable in some locations, while in others the induced current is strong enough for operators to disconnect their batteries and continue sending messages using electricity generated by the geomagnetic storm itself. This strange success does not make the event harmless. It shows that the storm is capable of driving current through human infrastructure over great distances. The telegraph system is the only widespread electrical network available to receive that energy, and it reacts across multiple regions. Had the same event occurred in a world filled with high-voltage transmission lines, satellites, digital timing systems, and global communication, the pathways would have been far more numerous. Yet the Carrington event should not be treated as a perfect model of modern catastrophe. The measurements are incomplete, the strength of the storm is still debated, and historical reports vary in reliability. Scientists estimate its intensity from old magnetograms, auroral observations, and telegraph records, but the instruments of the period are not designed for present-day analysis. Some measurements may saturate or contain timing uncertainties. The event is clearly extreme, though its exact place among all known storms remains open to refinement. This uncertainty matters because modern risk models often use Carrington as a benchmark. If its true magnetic intensity is overestimated, some scenarios become too severe. If important features are underestimated, infrastructure may be less prepared than assumed. History offers a warning, but not a complete engineering test. A more recent and better measured lesson arrives in March of 1989. The Sun releases several strong eruptions during a period of intense activity. A coronal mass ejection reaches Earth and triggers a major geomagnetic storm. Auroras appear far from the polar regions, and magnetic conditions change rapidly across North America. In Quebec, the power grid is especially vulnerable because long transmission lines cross regions of electrically resistant rock. Geomagnetically induced currents enter the network through transformer connections. Protective systems detect abnormal conditions and remove key equipment from service. The failures spread quickly. In about a minute and a half, the Hydro-Quebec grid collapses. Millions of people lose power, and the blackout lasts for roughly 9 hours. The event occurs during cold weather, disrupting homes, businesses, transport, and public services. Outside Quebec, utilities observe unusual currents, voltage instability, and transformer stress. A large transformer in the United States suffers serious damage. Satellites also experience anomalies, and radio systems are disturbed. The storm does not approach the likely strength of the Carrington event, yet it demonstrates that even a less extreme event can exploit real weaknesses in a modern network. The Quebec blackout becomes a case study because the chain of failure can be examined. The Sun releases an eruption. The magnetic field carried by the solar wind couples with Earth's field. Currents strengthen in the ionosphere. Magnetic conditions change at the ground. Voltage is induced along transmission lines. Transformers absorb unwanted current. Protection systems respond. The grid loses the balance required to remain stable. Each step follows known physics, but the speed of the collapse leaves little room for improvisation. The lesson is not that protective systems fail to work. They act according to the conditions they detect. The problem is that several protective actions occur across an interconnected network in a way that removes too much support at once. A device that saves one component can contribute to a larger blackout if the system around it is already unstable. Later changes improve awareness, monitoring, and procedures. Grid operators develop better models of geomagnetic currents. Space weather agencies provide alerts. Utilities examine transformer design, grounding, system loading, and emergency response. Yet the event remains relevant because electrical networks continue to evolve. Transmission distances grow, demand changes, renewable generation adds new patterns of power flow, and digital control becomes more important. The grid becomes more observable and adaptable, but also more dependent on communication, software, and precise timing. Carrington and Quebec therefore offer two different kinds of evidence. The first reveals the scale of a rare solar storm at the dawn of electrical technology. The second reveals the sensitivity of a mature power network to a storm that is strong but not unimaginable. One event is dramatic and historically incomplete. The other is modern, measured, and operationally specific. Together they show that the danger is neither pure speculation nor a simple replay of the past. The next severe storm will meet a civilization unlike the one that watched auroras in 1859, and unlike the one that lost power in Quebec in 1989. It will encounter satellites in crowded orbits, undersea communication links, high-voltage grids spanning continents, automated financial systems, aircraft dependent on navigation signals, and supply chains coordinated through continuous data. Some systems are better protected than their predecessors. Others introduce new dependencies that have never been tested under a truly extreme geomagnetic disturbance. History cannot provide a complete forecast because technology changes faster than the sun. It can only show that the physical pathway is real. A bright flash above a sunspot can be followed by a magnetic storm at Earth. A changing field can drive current through long wires. A regional network can collapse in little more than a minute. The interval between cause and consequence can be brief, but the chain connecting them may stretch from the solar corona to a control room on Earth. The warning contained in these events is quiet but persistent. Civilization does not need to be struck directly by solar plasma. It needs only to be connected by conductors while the magnetic field beneath them begins to move. A prolonged electrical failure does not remain an electrical problem for long. The first darkness may seem simple. Lights go out, screens turn black, elevators stop, and machinery falls silent. Yet modern civilization uses electricity not as one service among many, but as the hidden current joining nearly every service together. Water systems depend on pumps, fuel systems depend on controls, payment networks, and powered valves. Hospitals depend on ventilation, imaging, sterilization, refrigeration, and digital records. Communication depends on towers, routers, exchanges, satellites, and data centers. Food depends on cold storage, processing plants, transportation scheduling, and warehouse automation. When the grid fails across a wide region, these systems do not collapse at the same moment. They begin to fail in layers, each one placing pressure on the next. Backup power creates a temporary bridge. Batteries keep communication equipment alive for a limited period. Generators start at hospitals, emergency centers, water plants, and data facilities. Some systems continue almost normally, creating the impression that the outage is under control. But backup systems are designed mainly for local and temporary emergencies. They require fuel, maintenance, cooling, and staff. A geomagnetic storm that damages major transformers or interrupts several networks at once creates a different kind of crisis. The grid may not return before batteries are exhausted and fuel tanks begin to empty. Roads may be blocked by failed signals or heavy traffic. Fuel depots may have fuel in storage but no electricity to operate pumps. Refineries may shut down safely and require careful procedures before restarting. The machines intended to support recovery become dependent on the same infrastructure that has failed. Water is among the first essential systems to reveal this dependence. Municipal water often moves through a combination of gravity and electric pumping. Treatment plants use powered equipment to filter, disinfect, test, and distribute water. In some areas, reservoirs provide pressure for a time. In others, pumping stations must operate continuously. When backup power weakens, pressure drops. Upper floors lose service first. Firefighting becomes more difficult. Wastewater systems face a parallel problem. Sewage pumps stop, treatment slows, and untreated water may overflow into rivers or streets. Public health risks grow, not because the solar storm directly contaminates water, but because electricity no longer sustains the barriers that keep clean and waste systems separate. Hospitals are designed to endure outages, but their resilience has limits. Emergency generators protect critical circuits. Not every room or machine. Fuel must be delivered. Cooling systems must continue, especially in hot conditions. Electronic records may become inaccessible if communication links fail. Laboratories may lose temperature control. Pharmacies may struggle to verify prescriptions. Dialysis centers, nursing homes, and home medical devices create needs beyond major hospitals. Patients who rely on oxygen concentrators, powered beds, refrigeration for medicine, or electrically operated mobility equipment become vulnerable as batteries decline. Ambulances require fuel and functioning roads. Staff must reach their workplaces while also caring for families affected by the same outage. A health system that remains technically open can still become overwhelmed by failures outside its walls. Communication also weakens in stages. Mobile towers usually have batteries or generators, but heavy use increases demand just as backup time becomes limited. People attempt to call relatives, emergency services, employers, and authorities at once. Networks become congested. Internet service depends on powered equipment from homes to neighborhood cabinets and central facilities. Some fiber optic lines continue carrying signals, but the devices at their ends require electricity. Data centers may operate on generators, yet they need fuel and cooling. Satellite systems may already be disturbed by the same solar event, reducing navigation accuracy and weakening some communication links. Information becomes uneven. One district receives updates while another enters silence. Rumors spread more easily when official channels fail, and coordination becomes harder precisely when it is most needed. Food supply chains begin with stored inventory. Supermarkets may remain closed because lighting, payment systems, security, and refrigeration are unavailable. Cash machines may not work. Digital payments may fail even where goods remain. Cold storage warehouses can maintain temperature only while backup systems run. Milk, meat, medicine, and frozen food begin to spoil. Farms are not isolated from the crisis. Modern dairy operations use electric milking systems and refrigeration. Greenhouses rely on climate control. Livestock facilities need ventilation and water pumps. Grain can remain stable, but processing and transport depend on powered machinery. Fields may hold food while cities experience shortages because the chain between them has broken. The problem becomes one of movement and coordination rather than absolute scarcity. Fuel adds another layer. Gasoline and diesel are stored in tanks, but station pumps require power. Electronic payment and inventory systems may be unavailable. Emergency generators consume the same fuel needed by ambulances, repair vehicles, water plants, and communication towers. Authorities may establish priority distribution, but that requires functioning records, transport, and security. Ports and rail networks depend on signals, cranes, switching systems, and scheduling platforms. Trucks require fuel and reliable routes. If navigation signals are degraded, drivers and aircraft lose part of the precision on which modern logistics relies. A widespread outage slows the movement of replacement equipment just as demand for that equipment rises. Finance is vulnerable in a quieter way. Banks hold records across redundant systems, but access depends on communication and power. Markets may close to prevent disorder. Electronic transfers, card payments, payroll, and business accounting may be interrupted. Physical cash becomes useful but limited. Shops cannot easily price, record, or restock goods. Employers cannot confirm when systems will return. Insurance claims multiply while inspection and payment networks struggle. Economic damage grows each day, not only from broken machines but from work that cannot be performed, goods that cannot be moved, and trust that begins to weaken. The grid itself becomes harder to restore under these conditions. Power systems normally restart through a carefully controlled process. Some generating stations can start without external electricity. But many require power from the grid to run pumps, controls, and support equipment. Operators use black start resources to energize sections gradually, balance generation with demand, and reconnect regions without causing another collapse. If communication is degraded, transformers are damaged, and transportation is disrupted. This process slows. Large transformers cannot be replaced like household appliances. They may require custom manufacture, special rail transport, reinforced roads, cranes, and trained crews. Spare units help, but they are limited and may not match every location. Damage across several countries could create competition for the same components and materials. The crisis becomes international, even when the storm's physical effects vary by region. Cascading failure does not mean every system inevitably collapses. It means that the failure of one system increases the stress on others. A water plant without grid power consumes generator fuel. Fuel delivery requires transport. Transport requires communication and functioning roads. Communication requires backup power. Hospitals depend on all of them. Each connection forms a loop, and the loops can either support resilience or spread weakness. Preparation breaks these loops by adding independent supplies, manual controls, local generation, spare equipment, and clear priorities. Without such measures, the system becomes efficient in normal times but brittle under prolonged stress. The social effects depend on duration and trust. A short blackout produces inconvenience and local disruption. A longer outage changes behavior. People search for water, fuel, food, medicine, and reliable information. Emergency services receive more calls than they can answer. Families leave dark buildings or travel toward areas believed to have power. Traffic increases while signals are inactive. Heat or cold can turn inconvenience into danger. Public order does not vanish automatically. But uncertainty magnifies pressure. Communities with clear information, local resources, and trusted institutions respond differently from those left without guidance. The hidden threat to civilization is therefore not a single dramatic moment when every machine stops. It is the slow widening of dependency after the initial storm has passed. The sun may already appear quiet again while transformers remain damaged. Satellites recover, fuel runs low, and supply chains struggle to restart. The eruption lasts hours. The geomagnetic storm may last days. The consequences can continue far longer because recovery depends on the same network of electricity, communication, transport, and industry that has been weakened. In the most difficult cases, restoration becomes a race between the return of essential services and the gradual exhaustion of reserves that were never intended to sustain entire regions. Civilization does not fall because one wire carries an induced current. It becomes vulnerable when millions of systems, each designed to rely on the others, begin waiting for power that cannot yet return. The greatest uncertainty surrounding solar storms is not whether they can disrupt civilization, but how severe the next extreme event might become, and how often such an event is likely to occur. The evidence is real, yet incomplete. Instruments have watched the sun closely for only a small fraction of its life, and modern electrical systems have existed for an even shorter time. A few decades of satellite measurements cannot capture every rare possibility in a star that changes across centuries and millennia. Historical records extend the view, but they are uneven. Auroral reports, magnetic traces, damaged telegraph lines, and chemical signatures preserved in natural archives all offer clues, though none provide a perfect reconstruction. The danger, therefore, sits inside a wide range of estimates. Some models suggest that even a severe storm would cause temporary blackouts, satellite failures, and costly but recoverable disruption. Other models warn that certain combinations of field direction, speed, duration, geology, and grid design could damage enough large transformers to prolong outages for months or even years. The difference between these outcomes is not created by disagreement over basic physics. It arises from uncertainty about scale, timing, infrastructure, and how many failures occur at once. A storm strong enough to disturb one region may leave another largely untouched. A storm that passes quickly may produce brilliant auroras but limited damage. Another event of similar apparent size may carry a magnetic field that remains aligned against Earth's field for many hours, allowing energy to enter the magnetosphere without relief. The hidden structure inside the cloud matters as much as the cloud's visible size. That structure is difficult to measure before arrival, which leaves forecasts with a final interval of uncertainty, even when the eruption is clearly directed toward Earth. One of the clearest reminders of this uncertainty comes from a powerful solar eruption in July of 2012. A fast coronal mass ejection crosses Earth's orbit, but the planet is not there when it arrives. Spacecraft measurements show that the event is unusually strong, and that an earlier eruption may have cleared part of the solar wind ahead of it, allowing the later cloud to retain greater speed. Had Earth occupied that part of its orbit at the wrong time, the resulting geomagnetic storm might have been severe. The event becomes known as a near miss, though the phrase can be misleading. The sun does not fire at a fixed target, and Earth does not narrowly escape through intention or luck alone. The planet simply moves through an orbit while eruptions expand into space. Most miss because space is immense and the direction of each event is limited. Yet a near miss reveals that the required energy is present in the modern sun. An extreme eruption does not belong only to the 19th century or to ancient records. It can occur during an era of satellites, power grids, and global digital dependence. Estimating the probability of such events is difficult because rare storms are, by definition, rarely observed. Researchers often study the distribution of weaker events and extend the pattern toward larger ones. This method can suggest how frequently an event beyond the measured range might occur, but it depends on whether the same statistical pattern continues at the highest energies. The sun may have physical limits that make the strongest eruptions much rarer than a simple extension predicts. Alternatively, the short observing record may omit events that occur only once in many centuries. One widely discussed estimate proposes a chance of roughly 1 in 8 that a Carrington-class event could occur within a decade. That figure is not a countdown and does not mean each decade carries a guaranteed independent threat with perfect precision. It is a statistical estimate built from limited data and assumptions about the distribution of extreme storms. Other studies produce different probabilities. The correct value remains uncertain, but the central conclusion survives the risk is neither constant nor zero. and the passage of quiet years does not remove it. The Sun can remain calm through one solar cycle and active through another. Strong storms cluster around periods of greater activity, yet large eruptions can appear outside the expected peak. A low-probability event can remain unlikely on any particular day, while becoming increasingly plausible across the lifetime of infrastructure. Beyond the familiar category of severe geomagnetic storms lies the more unsettling question of superflares. Astronomers observe other stars similar to the Sun producing eruptions far more energetic than the largest events measured in the modern solar record. These stellar flares release immense bursts of radiation, sometimes hundreds or thousands of times stronger than ordinary large solar flares. At first, such behavior seems to belong mainly to younger, faster rotating, and more magnetically active stars. Yet observations also identify rare, powerful eruptions on stars that appear quieter and more Sun-like. This does not prove that the Sun will produce an identical event, nor does it establish how often such an eruption might occur. Stars that resemble the Sun in temperature and brightness may still differ in age, rotation, magnetic history, companions, or unseen features. Comparison reveals possibility, not certainty. The Sun's known behavior remains the primary guide, and its direct record contains no confirmed modern superflare on the most extreme stellar scale. Even so, natural archives suggest that Earth has experienced bursts of high-energy particles larger than any measured during the satellite era. Tree rings and polar ice preserve sudden increases in certain radioactive forms of carbon and other elements. These isotopes form when energetic particles strike the atmosphere and trigger nuclear reactions. Some sharp increases, including events in the 8th century and the 10th century, are consistent with exceptionally strong solar particle storms, though the exact solar conditions that produce them remain under study. They do not automatically prove that a gigantic coronal mass ejection struck Earth, or that a global technological catastrophe would have followed. Particle radiation, flare intensity, and geomagnetic impact are connected but not identical. An event can produce an enormous particle signal without carrying the magnetic orientation needed for the worst grid effects. The archives therefore widen the known range of solar behavior while preserving uncertainty about consequences. The possibility of a true superflare raises a deeper question about physical limits. Magnetic energy must be stored before it can be released. The maximum size of an eruption depends on the strength of the magnetic field, the area covered by active regions, the complexity of those fields, and the amount of free energy available above the surface. The Sun has produced sunspot groups larger than Earth many times, but the most extreme stellar superflares may require active regions or field strengths beyond anything observed on the modern Sun. Some models suggest that the Sun is physically capable of eruptions larger than the Carrington Event, though the most extreme cases may occur only across very long intervals. Others argue that direct comparisons with active stars overstate the likely solar maximum. The disagreement is not a choice between safety and catastrophe. It is an effort to define the boundary of what the solar dynamo can actually build. Even if the Sun never reaches the highest energies seen on other stars, civilization still faces serious risk from events well within the known solar range. A storm does not need to sterilize Earth, strip the atmosphere, or send humanity into permanent darkness to become historically important. It needs only to damage a limited number of critical systems at the same time. The language of apocalypse can obscure this more realistic danger. Solar storms do not threaten to burn away the oceans or instantly return the planet to a primitive age. The atmosphere and magnetic field continue protecting life. Most machines survive. Many regions retain power. Recovery begins. Yet a severe event can still create enormous economic losses, interrupt communication, damage satellites, and force controlled or uncontrolled blackouts across wide areas. The outcome depends as much on preparedness as on solar energy. A well-protected grid may convert an extreme storm into a difficult emergency. A poorly prepared network may turn a weaker event into a cascading failure. This makes uncertainty itself part of the threat. When estimates vary, decision makers may delay expensive protection because the worst case seems too speculative. At the same time, exaggerated claims can produce fatigue and distrust. The challenge is to prepare for a range of credible events without pretending that the exact probability is known. The sun offers warnings through active regions, flares, and travelling clouds, but it does not reveal the full scale of the next storm in advance. Civilization therefore stands beneath a star whose ordinary behaviour is well understood and whose rare limits remain only partly mapped. Somewhere between the quiet solar wind and the largest stellar superflares lies the true boundary of danger, and the observing record has not yet been long enough to show where that boundary rests. Preparation begins with attention. The sun cannot be prevented from producing flares, particle storms, or coronal mass ejections, and no technology can push an eruption away from Earth once it is already moving through space. The practical choice is therefore not control but readiness. Civilization can watch the star, estimate the path of an eruption, measure its magnetic structure as it approaches, and reduce the number of systems exposed at the most dangerous moment. This work already exists in observatories, forecasting centres, satellite control rooms, power utilities, aviation networks, and emergency agencies. It is less dramatic than the storm itself, but it is where most of the danger can be changed. A solar eruption may be natural and unavoidable, yet its consequences are shaped by engineering decisions made long before the sky brightens with aurora. The first layer of preparation is observation. Space-based instruments watch the sun in visible light, ultraviolet radiation, X-rays and radio wavelengths. They map sunspots, track magnetic complexity, and detect the sudden brightening of flares. Coronagraphs block the brilliant solar disk so that expanding clouds in the corona can be seen against the darker space around them. When a coronal mass ejection appears, forecasters estimate its speed, width, and direction. An eruption near the centre of the visible solar face may be more likely to move toward Earth, while one near the edge may travel mostly aside. Yet the geometry remains uncertain, because a three-dimensional cloud is being judged from distant images. Models help reconstruct its likely shape and arrival time, but no model removes every ambiguity. The warning may begin with a broad forecast measured in days, then become more precise as the cloud approaches. The next layer is direct measurement in the solar wind. Spacecraft positioned between Earth and the Sun sample the plasma before it reaches the magnetosphere. They measure speed, density, temperature, and magnetic direction. These readings reveal whether the incoming field is likely to couple strongly with Earth's field. If the magnetic orientation turns into the more dangerous direction and remains there, the expected geomagnetic storm becomes more serious. The final warning may be short, but even a brief interval can matter. Grid operators can change how electricity moves through the network. Satellite controllers can postpone sensitive operations or place spacecraft in safer configurations. Airlines can reconsider polar routes. Communication services can prepare for radio disruption. Emergency managers can alert key facilities that conditions may worsen. Readiness does not require certainty. It requires decisions that remain useful across several possible outcomes. The electrical grid offers some of the clearest protective options. Transformers and long transmission lines do not need to remain in their normal configuration while a severe storm passes. Operators can reduce power transfers across vulnerable routes, increase reserves, and temporarily remove selected equipment from service. In extreme cases, a controlled outage may be safer than allowing uncontrolled currents to push transformers toward failure. Such a decision carries obvious costs. Hospitals, businesses, homes, and transportation systems depend on uninterrupted electricity. Yet a short, planned reduction can be preferable to the destruction of equipment that takes months to replace. The difference is similar to closing a bridge before a flood rather than waiting for the structure to be swept away. The closure is disruptive, but the bridge remains available when the water falls. Controlled disconnection is only one measure. Networks can be designed to provide alternative paths for power, allowing operators to redistribute loading when geomagnetically induced currents begin to rise. Monitoring devices can measure those currents directly at transformer connections. Better models can combine real-time space weather data with local geology and grid configuration, identifying which regions are likely to experience the greatest stress. Transformers can be built or modified to tolerate unusual current more effectively. Protective relays can be adjusted so that they respond to genuine danger without unnecessarily removing too many components at once. Devices can limit the entry of unwanted direct current into parts of the network. None of these measures eliminates all risk, but together they make a cascading failure less likely. The cost of preparation is often smaller than the cost of widespread damage, especially when upgrades are included during ordinary replacement and maintenance rather than added only after a crisis. Satellite resilience requires a different set of defenses. Spacecraft can be shielded against radiation, though shielding adds mass and cannot stop every energetic particle. Electronic systems can be designed with redundancy so that a single corrupted component does not disable the entire craft. Computers can detect and correct some data errors caused by radiation. Operators can place satellites into safe mode, shutting down sensitive instruments and orienting the spacecraft to reduce risk. Navigation and communication networks can use multiple satellites and ground stations so that the loss of one element does not end the service. Low-orbit spacecraft can carry enough fuel or propulsion capacity to correct for storm-increased atmospheric drag. Tracking networks can update orbital predictions as the upper atmosphere expands. These measures turn space weather from an unexpected shock into a condition that the spacecraft is designed to endure. Human spaceflight requires still greater care because the crew cannot be replaced like damaged electronics. Vehicles traveling beyond the strongest protection of Earth's magnetic field need radiation monitoring and sheltered areas surrounded by water, supplies, fuel, or other mass capable of absorbing part of an energetic particle storm. Mission plans can limit the time spent outside shielding when solar activity is high. Forecasting can never guarantee complete warning, especially for the fastest particles, so the habitat itself must provide protection. The same principle applies throughout civilization. Warning is valuable, but resilience must remain when warning is incomplete. Ground systems also need the ability to function without their most fragile dependencies. Hospitals, water plants, communication hubs, and emergency centers can maintain backup generation, but the backup must be tested, fueled, and supported by realistic supply plans. Batteries can bridge the time before generators start. Local power sources can keep critical services operating if the wider grid is unavailable. Manual procedures can preserve basic functions when digital control systems fail. Spare communication channels can connect agencies when mobile networks become congested or satellite links weaken. Water storage, fuel reserves, and replacement equipment can slow the cascade from one failure into many. These preparations are not unique to solar storms. They also help during hurricanes, earthquakes, fires, cyber incidents, and ordinary equipment failures. This overlap makes space weather resilience especially practical. Investment in stronger systems does not wait idle for one rare event. It improves response to many kinds of disruption. International coordination matters because solar storms do not respect political borders. The same magnetic disturbance can affect grids, satellites, aviation routes, and communication systems across many countries. Forecast data must move quickly between observatories, governments, utilities, and operators. Standards for alerts should be clear enough that different organizations understand what action is expected. Spare transformers and specialized repair equipment may need to cross borders. Satellite data from one nation may help protect infrastructure in another. The storm is global, but vulnerability is uneven. So preparation depends on sharing information without assuming that every region faces the same conditions. Local geology, grid design, latitude, and infrastructure age all change the risk. A useful warning must therefore be broad enough to reach everyone and specific enough to guide local decisions. Public communication also requires restraint. Exaggeration can be almost as damaging as silence. Claims that a solar storm will inevitably end civilization create fear without improving readiness. Reassurance that nothing serious can happen creates the opposite problem. The accurate message lies between them. The atmosphere and magnetic field protect life at the surface from the worst direct effects. Most solar storms pass without major disruption. Even strong storms can often be managed. Yet rare events can threaten technology on which modern society depends, and preparation reduces that threat. Clear communication supports practical action, conserving backup power, protecting sensitive equipment, following official updates, and avoiding unnecessary strain on communication networks. Panic is not a defense. Information is. The sun will remain restless. Its magnetic cycle will rise and fall. Active regions will form, and eruptions will continue to cross the solar system. No final upgrade can remove that reality. Readiness is an ongoing practice, renewed as technology changes and as scientific understanding improves. The hidden danger becomes less hidden each time instruments detect a flare, models track a cloud, operators measure induced current, or engineers strengthen a transformer. Civilization cannot make the star quiet, but it can become harder to surprise. Beneath the same warm light that supports forests, oceans, cities, and fields, preparation creates a second kind of protection, built not from atmosphere or magnetism, but from knowledge, planning, and the willingness to act before the invisible storm arrives.